continuing with what we were talking about in our last video, right? Recall that we said that our KEQ used our equilibrium concentrations and that our reaction quotient, capital Q, used the initial concentrations, all right? Now, if we compare K and Q, it's going to tell us something very interesting about the direction that our reaction happens, okay? Remember we said that these reactions are in equilibrium, right? So sometimes they're going to go forward and sometimes they're going to go backward, all right? So if Q, our reaction quotient, is equal to our equilibrium constant, then we're going to be at equilibrium, right? So there's going to be no shift, all right? Now, that would be like saying, okay, if what we started with, right, Q is our initial concentrations. What we started with were like the two classrooms, right? If they're balanced already, if they're already in equilibrium, then there's going to be no shift, okay? Now, what happens if Q, what we started with, has a lot more products? Well, if we have a lot more products, right, remember that Q is equal to our concentration of products over our concentration of reactants, right, raised to their stoichiometric coefficients, okay? Now, if we have a lot of products, right, then Q is going to be really, really big relative to KEQ. So if Q is bigger than K, we're going to have more products than reactants initially. That means that we're going to have a lot more on the right-hand side, which if we want to balance, right, then we're going to have to shift to the left toward the reactants. So some of these students are going to have to move over into the other classroom to establish the equilibrium, okay? On the other hand, if Q is less than K, right, then that means that what we start with, we have very few products and a whole lot of reactants, okay? So we're going to have a lot of reactants, more reactants than products at the beginning, which means that in order to establish the equilibrium, we're going to have to shift to the right toward the products, okay? That means that we can use this ability to compare Q and K to tell us which way a reaction is going to proceed or shift based on the concentration at that particular time, okay? So let's do an example, all right? Moving on to slide 17. Let's say that we have a Kp equal to 2.4 times 10 to the third for a particular reaction, which says that 2NO gas is in equilibrium with N2 gas and O2 gas, all right? Let's say that we collected data for our partial pressures for 3 different trials, okay, where we started out with 3 different initial partial pressures, okay? Now, what is the shift going to be for each trial, okay? So if we want to find the shift for each trial, all right, let's take a look at trial 1. Again, this data is going to be in the upper right hand of slide 17, okay? Looking at trial 1, all right, let's write our reaction quotient, right, to figure out if we're in equilibrium, right? We're going to take our initial concentrations or our initial partial pressures, okay? Because remember, we can either represent K or Q as concentration or pressure. So in this case, we're going to have a little QP, okay? And that's going to be equal to our concentration of our products, right? N2 raised to the first, and we have O2 raised to its stoichiometric coefficient, which is 1. All right, divided by our concentration of NO initially, raised to the first, right? That would be for concentration, right? Now, if we wanted to do it in terms of partial pressure, right, how would we do that? Well, the exact same, right? QP is equal to our partial pressure of our product, so PN2 raised to the first, PO2 raised to the first, all divided by PNO raised to the second, because again, that's my stoichiometric coefficient, okay? So I have this expression, so now I know that I can calculate Q by simply plugging in my partial pressures, just like before, right? So we have PNO, which is 0.01 atmospheres squared, because its stoichiometric coefficient was 2. Then we have, for our partial pressure of N2, that was 0.11 atmospheres to the first, and then we have our partial pressure of O2, which is 2 atmospheres raised to the first. Plugging all of that in, don't forget about your 2 in the denominator, What you'll get is 2.2 times 10 to the third. Okay? Now, we know that our Kp was equal to 2.4 times 10 to the third, and this is 2.2 times 10 to the third. That means that Q for trial 1, Q for trial number 1 is less than my K. Now, if Q was less than K, then that means we have more reactants than products, all right? And that means we're going to shift to the right to balance out. All right? So again, when Q is less than K, we're going to shift to the right to make more product. Okay? So that was for trial 1. All right? Now, looking at trial 2, we're going to solve for Q the same way. Okay? Now, Q for number 2, that was going to be equal to, we take our partial pressure for our products, right? We have P of N2 times P of O2, both to the first. Don't forget about that. And we have P of NO to the second. Notice that the Q didn't change symbolically, but we did change our partial pressures. Okay? So in trial 2, I'm just going to plug in those numbers. PN2 was 0.36 to the first. Then we have our O2, which is 0.67 to the first. And then in the denominator, we had our NO, which was 0.0078 to the second. All right? Which meant that our Q for number 2 was equal to, that's funny, was equal to 4.0 times 10 to the third. All right? Comparing that to our Kp, we see that Q, 4.0 times 10 to the third, that's bigger than my K. Okay? And when we're bigger than K, that means we have more products than reactants initially. So we will shift to the left or shift to the reactants. Okay? Now, that was for trial 2. Trial 3. All right? Again, the Q expression doesn't change, but our initial concentrations or partial pressures do. So I'm just going to plug in those numbers. Notice that we plug in our P for our nitrogen, which is 0.51 raised to the first. Then we have our O2, which is 0.18 raised to the 1, right? Both those are raised to the first because those are the stoichiometric coefficients. And then we take our partial pressure of NO, which is 0.0062. We raise that to the 2 because its stoichiometric was 2. Now, plugging all of that in, we find that our reaction quotient for trial number 3 was equal to 2.4 times 10 to the third. Okay? You may have to round a little bit, all right? But notice that that was equal to K. And if we were equal to K, we found that we were at equilibrium, so there was going to be no shift, all right? We'll have lots of different examples for things like, or not lots of examples, we'll have lots of different problems in the homework as well as on your quizzes and exams that may look like some of this, all right? So make sure that you understand how to do that. Now, the next thing that I want to talk about is going to be one of the biggest topics that we talk about this semester. Okay, it will appear over and over and over in our next several chapters, and it will become very, very important that you understand how to do these problems systematically at the beginning, because the problems that we cover later will become increasingly difficult. All right, so I'm going to introduce the tools in this video. All right, we'll go through one example, and then in the next video, I'll talk to you guys about several other examples. All right, now, the very first thing for this we will do is going to be on slide 18, right? And this is going to be where we outline the rules for solving equilibrium problems. These are super important in chemistry, right? Now, the steps for this, the first thing you're going to do is write a balanced chemical equation. The second thing that you're going to do is you're going to write the equilibrium expression. Okay, that's going to be like your K. All right, symbolically. All right, the next thing is going to be to list the initial concentrations. Okay, then for step 4, you will calculate your reaction quotient Q and determine the direction of the shift. Your 5th step will be to define the change needed to reach equilibrium. Okay? And the way that you do that is by something called an ICE table. Don't worry, I'll show you how to do that. Step 6, you're going to substitute your equilibrium concentrations into the equilibrium expression that you came up with above. I will talk to you about the 5% rule. All right. And then the 7th step is going to be to check your K. All right. Now, I do mine a little bit differently than the way that they've outlined here, okay? You can do them either way, all right? But you'll need to make sure that you're consistent in the method that you use, okay? So if we do the example on slide 19, okay? In the example, it says that Lexan is a plastic used for eyeglasses, okay? And it contains phosgene. Okay, now phosgene is COCl2, and phosgene decomposes by this reaction. So we have COCl2 in equilibrium with CO plus Cl2. Okay? And it has a Kp equal to 6.8 times 10 to the negative 9 at 100 degrees Celsius. All right? Now, if pure phosgene has an initial partial pressure, so that's the partial pressure COCl2 initially equal to 1.0 atmospheres. All right, then calculate the equilibrium pressure of all the species. Okay, that means all the chemicals. All right, now the first thing that you always want to do, write the reaction. Okay, again, you're going to write the reaction. We have it. It's CO, Cl2 in equilibrium with CO, Cl2. CO plus Cl2. Okay, so that is our reaction. The second thing that you're going to do is you're going to write your equilibrium expression. Okay, now your equilibrium expression, as I said before, that's going to be your symbolic K. All right, so we have K, and that's equal to, since we're dealing with partial pressures, it's probably a good idea to write K as partial pressure, so we have P of CO, right? That's one of our products, raised to the first. We have the partial pressure of Cl2 raised to the first because that's a stoichiometric coefficient. And then we have our partial pressure of COCl2 also raised to the first. Okay, so that's our equilibrium expression. The third thing that you're going to want to do is to list your initial concentrations. Okay, so your initial concentrations, or in this case, partial pressures. Okay, so we know that we have an initial concentration PCOCl2, right? We know that our initial concentration, our initial partial pressure is 1 atmosphere. Okay, so we've done step 3. Step 4. Oh, sorry. Now, before we move on to step 3, notice that there isn't any information about any of the other species. Okay, that means that they probably are 0. Okay, so that means that P of CO is equal to 0 atmospheres, and our P of Cl2 is equal to 0 atmospheres. Okay, we were able to deduce that because it wasn't given above in our description of the problem for our initial concentrations or initial partial pressures. Okay, so you can assume that they're 0 if they don't tell you in the problem statement. All right, now step 4 is to write Q and determine the shift. Okay, I'm going to erase these so that we can continue. Now, since I'm going to write Q, right? Q is equal to, right? We define it as this, right? It's our partial pressure of CO times our partial pressure of Cl2 all over our partial pressure of COCl2. Okay? Now, we know that the partial pressure of CO is 0 atmospheres. We know that our partial pressure of Cl is 0 atmospheres. And we know that our partial pressure of PCl, or our partial pressure of COCl2 is equal to 1 atmosphere. Well, that's easy. That means our Q is 0, right? We've got our Kp, right? Q is much less than Kp, okay? And if Q is less than Kp, right, then that means that we shift to the products, right, or to the right, depending on how you like to define it, okay? So that is step 4. Step 5 is to set up an ice table. Okay? Now, when you set up an ice table, first thing you do is to write the reaction. So we've got COCl2 in equilibrium with CO plus Cl2. This is step A. Write the reaction. Okay? Now, the next thing that you're going to do is you're going to fill in lines that say I, C, and E. All right? Now, I stands for initial, C stands for change, and E stands for equilibrium. All right? And then you sort of build a table where you have the same number of columns as you do species in your reaction. Okay, so your rows are ICE, and you have however many columns are going to be the number of species. Okay, the next thing in line for part B, okay, 5 part B, is going to be to write your initial concentrations, okay, or your partial pressures. So we know that we had an initial partial pressure of 1 atmosphere, and these were 0 atmospheres. All right? Then we're going to fill in our change, okay? So we write the stoichiometric coefficient of that species times the change. Okay? That's going to be part C. Okay? Now, that would mean that we take our stoichiometric coefficient, which is 1, and our change is going to be negative x. Okay? Now, if it is a reactant, it is negative x. If it is a product, it is positive x. All right? Now, over here, our change, we take our stoichiometric coefficient times the change. Since it's a product, it will be plus x. Then we have our stoichiometric coefficient times our change, which is, since it's a product, plus x. Then, for part D, okay, we are going to write the result of addition. Okay, so we take this row, we add it to this one, and we get this one. So it's going to be 1.0 atmospheres minus or plus negative x, right? So I'm just going to say minus x because I took 1 and then I added the negative x, all right? Because I'm multiplying my stoichiometric coefficient times negative x. Here, I'm going to take 0, right? And then I'm going to add positive x, which means that it's going to be x, all right? Same thing here. I take 0 plus 1 times x, which is equal to x, all right? Now, that's step 5. Moving on to step 6. How are we on time? All right, so moving on to step 6. I'm going to speed this up a little bit. Now we're going to evaluate into our K expression, right? So we know that we have this K. So we're going to write our KEQ and we're going to plug in what we have for our equilibrium. Okay? So the very first thing, right, is going to be P of CO to the first, P of Cl2 to the first, all over P of CO, Cl2 to the first. Okay? I'm going to erase this stuff on the side. You guys already have that in your notes. Okay? And now I'm going to plug in my equilibrium values. My equilibrium values, right, I had the initial ones. Those were used to get Q. Now I have my equilibrium values. I know that I'm going to take my value for CO, and I'm going to plug that in. So that's X to the first. Then I'm going to take my value for Cl2 at equilibrium. Well, that's X. And I'm going to raise that to its stoichiometric coefficient. And then I'm going to put that all over my equilibrium value for my COCl3. I have 1.0 minus X, right? Now, so I've evaluated. So I'm then going to solve for X, okay? Because we know that our KEQ from the problem statement was equal to 6.8 times 10 to the negative 9. That means that's equal to x to the first, all over 1 minus x, which is equal to x squared over 1 minus x. All right? Now, at this point, okay, I'm going to cross multiply. All right, so I have 6.8 times 10 to the negative 9 times 1 minus x, right? I took my 1 minus x and I multiplied it over there, and I took the 1 that's on the denominator here and multiplied it by that, so I get x squared. Again, you're just cross multiplying this part. Okay, so I now have this expression. All right, then I get that x squared is equal to 6.8 times 10 to the negative 9 minus 6.8 times 10 to the negative 9 times x, because I distributed my 6.8 times 10 to the negative 9 times the 1 and the negative x. Okay, and I just flipped the signs. Now, I'm going to pull everything over to the left-hand side so that I have x squared. So I'm subtracting off the right-hand side. So I've got negative 6.8 times 10 to the negative 9 plus 6.8 times 10 to the negative 9x is equal to 0. Okay? Now, if I reorder this in orders of decreasing powers of x, right, that's x squared, that's x to the first, that's x to the 0, then I will have x squared plus 6.8 times 10 to the negative 9x minus 6.8 times 10 to the negative 9. All I'm doing is rearranging it, is equal to 0. That means that I have a, b, and c. All right, that quadratic equation is going to come in handy for y'all. All right, I know that a is equal to 1, b is equal to 6.8 times 10 to the negative 9, c is equal to negative 6.8 times 10 to the negative 9. All right, I plug that into my quadratic formula, which is x is equal to negative b plus or minus the square root of b squared minus 4ac. All right, this is covered in every high school algebra class in the country, so you guys should be able to do this pretty quickly. All over to a, you plug in a, b, and c, and what you will find is that you have 6.8 times 10 to the negative 9 plus or minus the square root of 6.8 times 10 to the negative 9, that is squared, minus 4ac, right? I don't think I'm going to go through all that. You guys know how to do that. If you don't, you can always ask me in the discussion sections or send me an email. All right. And what you will find is that x is equal to 8.2459 times 10 to the negative 5th and negative 8.2459 times 10 to the negative 5th. Now, we have these two as possible solutions. This one is negative. Okay. Since it is negative, right, we can't have a negative pressure. Right? So if we can't have negative pressure, we know that that is not our solution. Okay? So at this point, what you will need to do, so that was step 6. All right? Well, we are continuing, I guess, on step 6. All right, so now we know that x has to be equal to 8.2459 times 10 to the negative 5th. All right, now if you remember, x in our table was equal to our partial pressure of our CO at equilibrium. Right? The last value here, right? Remember in our ICE table, right, we had I, C, E. These values are at equilibrium, right? We had our COCl2 in equilibrium with our CO and with our CO, let me look at the table, and Cl2. Probably shouldn't have erased that right away, but we knew that this was x and 1 minus x. Okay, well, we solved for x. Okay, so that's our partial pressure of CO. It is also equal to our partial pressure of Cl2 at equilibrium, right? Because it's in the equilibrium line. All right, and then if we want to get our partial pressure of COCl2, notice that that is 1 minus x. So we take 1 minus x, which is equal to 1 minus 8.2459 times 10 to the negative fifth, all right, which gives us a partial pressure equal to which gives us a partial pressure of 0.9999 atmospheres. All right, now that means that we were able to get all of our partial pressures. The last step, of course, for step 7 would always be to check that you get your Kp. So all you would do is you would just plug in those values of partial pressure, right? Where we have PCO to the first, PCl2 to the first over PCOCl2 to the first. And that would give you, hopefully, if you plugged in those 3 values, that would give you the value of Kp, right? Which was equal to 6.8 times 10 to the negative 9. All right, don't worry, we will go through several more examples because I really want you guys to be able to do this. All right, good luck.